we'll start the second lecture now, and we will quickly see some theorems on limits that will seem very obvious to you. So let us start with theorems on limits. So first of all, let a comma b belongs to real numbers and being belonging to positive integers. So first is limit x tends to a, b is equal to b. It is very obvious because this is a constant. And second is limit x tends to a, x is equal to a, again very obvious. And third, limit x tends to a, x power n is equal to a power n, again it's very obvious. Now let f and g be two functions such that limit x tends to a of x is equal to l and limit x tends to a g of x is equal to n. Then first is limit x tends to a, k times fx is equal to kl, where k is independent of x. A constant factor may be taken outside the limit sign. And second is the limit of x tends to a, f of x plus g of x is equal to the sum of their individual limits, that is equal to l plus m. That is the sum of their individual limits. That means we can break it into limit x tends to a, f of x plus limit x tends to a, g of x. Okay, but here we should pay attention that limit of the sum of the two functions is equal to the sum of their individual limits. This will always hold. And third is just subtraction. That is limit x tends to a, limit f of x minus g of x is equal to l minus m. So I hope you have written it down. And now an important statement: the limit of an algebraic sum of 2 or 3 or in general any definite number of functions is equal to the algebraic sum of the limits of these functions. Even if there are fx, gx, hx, so on till n functions, we can use these theorems. Okay, and another obvious statement: limit x tends to a, gx upon fx is equal to m upon l. If and given that the denominator should not be 0, that is denominator should not be 0. And we would see in further, if both are 0, that is if it is a format of 0 by 0, it is an indeterminate format for which calculating the limits we use certain techniques that we would see in further modules. Okay, so moving forward, so now let us move on to some few examples. The first example 1, limit x tends to 2, x plus 2. Second, limit x tends to 2, x square plus 4 upon x plus 2. And third, limit x tends to 3, 2x square minus 10 cube root. And obviously its answer is 4. Its answer is 8 by 4 is equal to 2. And its answer is 2 into 9, that is 18, minus 10, 8, whole power 1 by 3 is equal to 2. And this method is also called as direct substitution method. And that is, we have just plugged in the value of a in place of x. So now moving forward, and now before moving forward, I would like to introduce a small topic, that is basic elementary functions. And now the following functions are called as basic elementary functions. First one, next to the power p, where p belongs to any real number. And second is y is equal to a power x, where a is any positive real number, not all real numbers, only positive. That is a is greater than 0. And third, y is equal to logarithm of x to the base a. And fourth, y is equal to any trigonometric function of x, that is sine, cos, tangent, etc. And inverse functions such as sine inverse, cos inverse, tan inverse, etc. These all functions are called basic elementary functions. An elementary function is one which may be represented by a single formula, y is equal to fx. Like here, everyone is represented by any single formula, okay? And where fx is made up of basic elementary functions and constants by means of finite number of operations of addition, subtraction, multiplication, division, or any other composition of them. And please note that piecewise defined functions are non-elementary. For example, gent x, fractional part of x, signum x are non-elementary functions. Gent x, fractional part of x, and signum x are non-elementary functions. Okay. And for review, this is a greatest integer function. This is the fractional part of x, and signum x is basically resembles the sign of x. This sign of not this sign, but actually the sign. That the x is positive, negative, or 0. The graph of signum x is like when x is greater than 0, its graph is y equal to 1. When x is less than 0, its graph is y equal to -1. And at x equal to 0, its value is 0. So this is a piecewise defined function. That is, the function is defined for first x greater than 0, then x equal to 0, then x less than 0. So these piecewise functions are not elementary functions. And now an important statement, that is, for all elementary functions, limit at any point in domain is equal to the function's value at that point. Because these functions are continuous, so the value in the neighborhood, that is limit at function as x tends to a will be equal to the function will be equal to the value of the function at that point. Okay. For example, limit x tends to 0, x cube plus 3x square minus x minus 3 whole divided by x square plus x minus 6. Since the given function is an elementary function and the polynomial in the denominator does not vanish at x equal to 0, that is, its value is not equal to 0, we obtain the limit by substituting x equal to 0 in the function directly. That is, we get minus 3 upon minus 6, that is equal to half, and that's our answer. So moving forward, and now an important note is that when a function is defined only on one side of the point a, then limit x tends to a f of x is identical with the one side limit if it exists. For example, let the function be fx equal to root x. Okay. From graph you can see the function is like this. It is always increasing function. Okay. So f is defined only at the right side of x equal to 0. So limit of x tends to 0 of root x is equal to 0, and we know that limit x tends to 0 of root x equal to 0. And we have already studied that for limit to exist, left hand limit should be equal to right hand limit. That is, limit of x tends to 0 minus root x equal to limit of x tends to 0 plus root x. But 0 minus is just behind x equal to 0, and we know that in this y equal to root x, the thing in under root should not be negative. This should be always greater than equal to 0. So this is not in domain. So in these cases we always calculate a one-sided limit, and these types of functions cannot have an ordinary limit at the endpoint of its domain. So it can have only one-sided limits. Okay. consider another example, that is limit x tends to 0 sine inverse e to the power mod x. Okay, even if we know that that here at x equal to 0 sine inverse this becomes sine inverse 1, that is equal to pi by 2. The function is undefined on both the sides of x equal to 0, hence there is no question of limit, because e per mod x is always greater than or equal to 1. But in sine inverse, but the domain of sine inverse t is t should belong from -1 close to 1 close, and in the neighborhood of x equal to 0, that is x equal to 0 plus and x equal to 0 minus, the sine inverse here, the inner value inside the function of sine inverse is always greater than 0, that is it is not in domain. So there is no question of that what should be limit, as limit does not exist. Though at x equal to 0 this is sine inverse 1, that is pi by 2, but while calculating the limit we don't it doesn't matter what is the value of the function at that point. We have to check in the neighborhood, and the neighborhoods of this function are not in domain, so it is clear that this function does not have any limit. And now quickly recapping the non-existence of limit that we have already studied, that is three of the most common types of behavior associated with non-existence of a limit are: first, fx approaches a different number from the right side as of a that it approaches from the left side. Second, fx increases or decreases without bound as x approaches a, that is increasing or decreasing without bounds means it approaches to plus infinity or minus infinity. Or the third case is if f of x oscillates too much as x approaches a. Example for my third statement, that is if fx oscillates too much as x approaches to a. For this, let us consider the example y equal to sine of 1 upon x, and we have to find its limit. X tends to 0 sine of 1 upon x. This is sine. So when we plug in the value of x equal to 0 in sine inverse 1 by x, we know that as x approaches to 0, 1 by x approaches to infinity. So sine of 1 by x, that is sine of infinity, and we know that we cannot say any particular value of that is sine belongs from, that is sine of t belongs from -1 to 1. So as t approaches to infinity, we cannot tell any specific value that sine t should have. So we say that as x tends to 0, this function is undefined. You may also check its graph also, and its sine in the graph of sine of 1 by x is something like this. And here when you check the graph, it is literally like this area is painted. So you can see that at x equal to 0 you cannot specify any particular value there, but you can say that it belongs from -1 to 1. So we say that limit does not exist, and I am using DNE as an abbreviation of does not exist. Okay, so now two important points, that is if fx is an even function, then we have limit f of x as x tends to 0 minus is equal to limit of f of x tends to 0 plus is equal to 0. Sorry, not equal to 0. Sorry. And second, limit of f of x tends to a minus is equal to limit of f of x tends to minus of a plus. Quite obvious. And now another important statement: if f of x, that is function of x, is an odd function, then firstly limit of x tends to 0 minus of fx is equal to negative of limit of f of x as x tends to minus of 0 plus and second is limit of second statement is limit of x tends to a minus f of x equal to minus of limit of x tends to minus times a plus f of x. And here further, if limit of x tends to and further here this can be extended that further if limit of x tends to 0 f of x exists, then limit x tends to 0 f of x is 0. That is, if limit exists at x tends to 0, then limit of f of x as x tends to 0 will be 0 if f of x is odd function. And to recap what is odd function and what is even function, and odd function is defined by if f of that is if f of x is a odd function, if f of minus x is equal to minus times f of x, that is if at x equal to a it has value of 2, and x equal to minus a it has value of minus 2. So it looks like this, and here the same thing with the magnitude would be absolutely same, just with the negative sign. And even function, it is further more obvious, that is f of minus x is equal to f of x. That is just a mirror image about y-axis. That is, at x equal to a it has value 2, and x equal to minus a it would also have the value 2. That is, it is just like a mirror image. So now these two statements will look like quite obvious for you. Okay. So I am having another good example, that is evaluate limit x tends to 0 gent of sine inverse x upon x, where this is the greatest integer function. So try this. And now from the graph of y equal to x, y equal to sin x, and y equal to sin inverse x, we can also say that this is the graph of y equal to sin x. This is the graph of y equal to x, and this is the graph of y equals to sin inverse x. That is sin inverse of x. This is sin x, and this is y equals to x. So clearly you can see that when x tends to 0, or for any value of x, when x is greater than 0, sin inverse x is greater than x is greater than sin x. And for all value of x, you can generalize that magnitude of sin inverse x is greater than magnitude of x is greater than magnitude of sin x. It is very clear from the graph. Like, you may draw a straight vertical line to see that for any value of x, sin inverse x is greater than x is greater than sin x. Okay. So now moving forward to the next page. As we already know that sin inverse of x upon x is greater than 1, and also sin inverse x upon x is an even function. And now we can say that sin inverse x upon x gen, we would check the right hand limits and left hand limits. And so by checking both, we would get answer as 1, that is limit x tends to 0. So this would be our answer. Okay. And for more explanation, here you can see that for limit x tends to 0 plus, that is right hand limit, that you already know. And for calculating left hand limit, you may put that is limit x tends to 0 minus of a function is equal to limit of x tends to 0 plus f of minus h. You must substitute x by minus h, that is x equal to minus h, and then calculate for limit x tending to 0 plus. So we try this also. In fact, you will get the same answer in both the cases, no matter what. So moving forward, now we would start with determinant and indeterminate forms. First of all, the determinant form. First is a determinant or you may also pronounce it as determinate. First is determinate form. It is a simple direct substitution that we have already done. So I don't think that I need to explain it much more. So we would come to indeterminate form. Indeterminate form. It is a form in which the limit cannot be predicted appropriately. Special methods are required to find the limit. In this case, two problems having the same form may not have equal formats and equal limits. That is, the limit. That is, for example, limit x tends to a f of x upon g of x, where this tends to 0 and this also tends to 0, is called an indeterminate form of type 0 by 0. And consider the following limits of the 0 by 0 form. First, limit x tends to 0, x square upon x. Second, limit x tends to 0. First is limit x tends to 0, x square upon x. Second is limit x tends to 0, x upon x. Third is limit x tends to 0, x upon x cube. Clearly, this would become x, and its answer would be 0, and its answer would be 1, and its answer would be plus minus infinity, or does not exist. We would preferably choose does not exist. Okay. But you may notice that all of the forms 0 by 0, 0 by 0, 0 by 0. So they have the same forms, but even though their limits are not same. So this is very important. We notice that the result varies quite significantly, even they are in the same indeterminate form. The word indeterminate here refers to the fact that the limiting behavior of the quotient cannot be determined without further study. The expression 0 by 0 is just a device to describe the circumstance of a limit of a quotient in which both the numerator and denominator approach 0. And now some few important indeterminate or indeterminate forms. Are first is 0 by 0, that we already know. Second is infinity by infinity, and third is 0 into infinity. Fourth is infinity minus infinity. Fifth is 0 past 0. This is infinity past 0, and seventh is 1 power infinity. And here you may be surprised that how this can be indeterminate, as 1 to power anything should be 1, infinity and anything to the power 0 should be 1. So how they are indeterminate? So now this is very important note, that please note that 0 here doesn't mean that exact 0, but it represents a value approaching towards 0, and the behavior of 1 and infinity are also similar. That is, this is not exact infinity. In fact, in exact infinity is not defined. Means infinity is just a symbol. Not going much into the depth of what is infinity, because it has a huge discussions. So coming on to the point, that is, these zeros, ones, etc., these all are tending to 1, tending to 0, tending to infinity. So these are not exact. That is, exact 1 to the power anything is equal to 1, and anything to the power exact 0 is equal to 1. So here it is exact 0, here it is exact 1, that we have studied in previous classes, that is 9 times etc. But here it is tending to 1, tending to infinity, tending to 0. So that's why these are indeterminate forms. Okay. Now, if limit of x tends to a of fx is equal to 0, and limit of gx as x tends to a is equal to infinity or minus infinity, it isn't clear that what the value of limit x tends to a f of x into g of x is, if any will be. There is a struggle between f and g. That is, it is an indeterminate form of 0 into infinity. Okay. If f wins, the answer will be 0. If g wins, the answer will be infinity or minus infinity. Or there may be a compromise where the answer is finite non-zero number. This kind of limit is called indeterminate form of type 0 into infinity. We can deal it with by writing the product f into g as a quotient. That is, it is obvious that we can write 0 as 1 by infinity. We can convert this by taking quotient. That is, if limit x tends to a, f of x is equal to 0. Then we can convert this by doing 1 upon 1 upon fx. So this it, so this can also be appropriated as 1 by infinity. So it is very obvious, and you can see that these three forms, that is 0 by 0, infinity by infinity, and 0 times infinity, these all three forms are interconvertible into each other. And we will also use this in our further modules also, particularly in the L'Hopital's rule. So moving forward to the next page, another important point to see is that is let y is equal to f of x to the power g of x. Then taking natural log on the both sides, natural log of y is equal to gx times natural log of fx, and raising to the power e, we will get e to power ln y, that is equal to y is equal to e to power ln of fx into gx. So we would frequently use this, and this is very important. Please learn this also. And important note here is that this would also be used in computing the formats of 0 to power 0, 1 to and infinity to the power 0, and 1 to power infinity. So please note that this is very important. Now having an example, 1 plus gent of cos x to the power 1 upon x square, limit x tends to 0. And obviously this is not an indeterminate form, not an indeterminate form, because here this is exact 1. So exact 1 to the power anything is always equal to 1. Okay. So another example, and tell does the function y equals to sine of 1 by x divided by sine of 1 by x tend to a limit as x tends to 0, that is or not. And please notice that in the numerator and denominator both are same. So its solution is that the function is equal to 1 and for every value of x when sine of but except 1, that is when sine of 1 by x is equal to 0, that is when x is equal to 1 upon pi, 1 by 2 pi, or 1 upon n pi, and so on. For these values, the formula for y assumes a meaningless expression that is 0 by 0, and y is therefore not defined for an infinitely many values of x near x equal to 0. So note that this is not the indeterminate form 0 by 0, and the limit does not exist. Okay. It might look very unobvious, but if you see the graph at x equal to 1 by pi, 1 by 2 pi, 1 by 3 pi, and so on, the value would not exist. So there would come open circles, except that there would be a straight line of y equal to 1. But for every value of x equal to 1 upon n pi, the function would not exist, as n tending to infinity, x tends to 0. So near x equal to 0, for infinite number of points, the function would be not defined, so hence the limit does not exist. And now moving forward, now we will discuss the method of factorization and cancellation of common factors. For example, limit x tends to minus 3, x square plus x minus 6 on x plus 3. Clearly it is the indeterminate form of 0 by 0. So we cannot apply direct substitution because the limit of denominator is 0. So direct substitution fails here. Because the limit of numerator is also 0. The numerator and denominator have common factor x plus 3. Thus for all x not equal to minus 3, we can cancel this factor to obtain it as x plus 3 times x minus 2 upon x plus 3. We will cancel it out the common factor. So we will get it as minus 5. Although correct, the second equality in the preceding computation needs some justification, since cancelling the factor x plus 3 alters the function by expanding its domain. However, the two functions are identical except at x equal to minus 3. And we know, and from our previous discussions, we know that this difference has no effect on the limit as x approaches to minus 3 because we are concerned with the neighborhood values. Okay. And now an important note. First, x to the power of n minus a power n is equal to x minus a into x to the power n minus 1 plus x power n minus 2 a plus x power n minus 3 a power 2 and so on till x power 1 a power n minus 2 plus a power n minus 1, or where n is even or odd integer. Okay. This is valid for all n where there are even or odd positive integers. And x power n plus a power n is equal to x plus a times x power n minus 1 minus x power n minus 2 a plus x power n minus 3 a power 2 and so on till plus minus 1 power n minus 1 a power n minus 1. And this is valid only for n belonging to positive odd integer. Okay. So for example limit x tends to 0 1 plus x cube fifth root minus 1 whole brackets. And for this, let us put 1 plus x equals to y power 5. And now this limit converts to limit y tends to 1 because as x tends to 0, y tends to 1. Okay, so it converts as limit y tends to 1 y cube minus 1 whole divided by y power 5 minus 1. So we can easily find this as limit y tends to 1 y minus 1 y square plus y plus 1 and y minus 1 y power 4 plus y cube plus y square plus y plus 1. And this we have done from this that we have studied now only. So clearly we would cancel it out, y minus 1 y minus 1, that is the common factor, and we would get our answer as 3 upon 5. That's our answer. Okay, moving on to the next page. And now I am having a good question, that is if limit x tends to 0 f of x upon x square is 2, then evaluate the following limits giving explicit reasoning. First, limit x tends to 0 gent of fx. Second is limit x tends to 0 f x upon x gent, where the square brackets are representing greatest integer function. Okay, try this, and I will start the solution after countdown 3 2 1. And now let's start the solution. And let L is equal to limit x tends to 0 gent of f of x is equal to limit of x tends to 0 f of x upon x square into x square is gent. So now argument of a greatest integer function is tending towards 0, and from positive side, as x tends to 0, f of x upon x square is 2 and x square tends to 0 plus, and we have f of x upon x square times x square tends to 0 plus. So that is, this is always greater than equal to 0. So and also as limit x tends to 0, this is 2 and this is 0 plus, so it is 0 plus, so gent of 0 plus is 0. And answer to the first part is 0. And now second part. From this we will clearly write it as f of x upon x square times x gent. This is 2 as limit x tends to 0, but as x tends to 0 plus, this is 0 plus, and as x tends to 0 minus, this is 0 minus. So as x becomes negative, this also becomes negative, although approximately 0, but just less than 0. and the greatest integer function of 0 minus, that is the number just less than 0, is equal to -1. That is the left hand limit. And for the right hand limit, as x tends to 0 plus, this tends to 0 plus, that is gent of 0 plus is equal to +1. And clearly left hand limit is not equal to right hand limit, so answer to the second part is limit does not exist. And now moving forward, now we'll come to the rationalization method. Rationalization method. And if in any limit the denominator or numerator involves the radical sign, then we can rationalize the irrational expression by multiplying with the conjugates to remove the indeterminacy. For example, limit x tends to 2 plus x minus 2 upon root x square minus 4 minus under root of x minus 2. Okay, give this problem a try. So now let's start with the solution. So for calculating this, we can multiply this with its conjugate, that is root x square minus 4 plus under root x minus 2, and same above to keep the expression same. And you know that a plus b times a minus b is equal to a square minus b square, that we already know. So it becomes x minus 2 times root x square minus 4 plus under root x minus 2 upon x square minus 4 minus x plus 2, limit x tends to 2 plus. Is equal to x minus 2 times under root x minus 2 whole common under root x plus 2 plus 1 upon x square minus x minus 2. Okay, so we can substitute this as x minus 2 times x plus 1, and this cancels out. And now putting in the limit x tends to 2 plus, this comes out to be 0, and that is the answer. Okay. Now another important note, that is x to the power 1 by n minus a to the power 1 by n times x to the power minus 1 upon n plus x to the power n minus 2 by n a to the power 1 by n plus x to the power n minus 3 a to the power 2 by n, so on, plus a to the power n minus 1 by n is equals to x minus a. This is the first note, and moving on to the next page. And the second important note is, if n is equal to odd integer and also positive, and x to the power 1 by n plus a to the power 1 by n times x to the power n minus 1 whole divided by n plus minus x to the power n minus 2 by 2 a to the power 1 by n plus x to the power n minus 3 by n a to the power 2 by n, so on, is equal to x plus a. Remember, it is only for when n is equal to an odd integer, that is positive. Okay, so moving forward, now comes the limit using expansion series of functions. In this method, basically we use the series expansion of sin x, cos x, tan x, logarithm of 1 plus x, a power x, e power x, etc. to evaluate the limit. Following are some of the frequently used series expansions that we are going to study. Okay, and first let me write the heading, that is expansion series. And giving you a general advice, if you remember this, it would be very beneficial for you, and by this you can solve any problem in just few seconds. Okay. So yeah, so first is a par x equal to 1 plus x ln a upon 1 factorial plus x square ln square a by 2 factorial plus x cube ln cube a by 3 factorial and so on until infinity, and it is valid for a greater than 0. Second is e par x is equal to 1 plus x upon 1 factorial plus x square by 2 factorial. You can simply substitute a as e, and ln e becomes 1, so it just becomes this series, so on. Okay. And third is natural log of 1 plus x equal to x minus x square by 2 factorial. So it is not factorial, it is just simply 2. It's x cube by 3 minus x by 4 by 4 and so on till infinity, and valid only for mod x less than equal to 1, or you may write x less than equal to minus 1 and greater than minus 1. And please note that here equality does not hold for x equal to minus 1. Okay, but here x equal to 1 equality holds. Okay. And for fourth, sin x is equal to x minus x cube by 3 factorial plus x bar 5 by factorial minus x bar 7 by sin factorial and so on. And fifth is cos x is equal to 1 minus x square by 2 factorial plus x bar 4 by 4 factorial minus x bar 6 by 6 factorial and so on. And sixth is 6 tangent of x is equal to x minus x cube by 3 plus it's plus x cube by 3 plus 2 times x bar 5 upon 15 and so on. Seventh is sin inverse x is equal to x plus 1 cube x cube upon 3 factorial plus 1 square, it is square 1 square 3 square x bar 5 by 5 factorial plus 1 square 3 square 5 square x bar 7 by 7 factorial and so on. And eighth is secant x is equal to 1 plus x square by 2 factorial plus 5 times x bar 4 by 4 factorial plus 61 x bar 6 by 6 factorial and so on. Ninth is tan inverse x is equal to x minus x cube by 3 plus x bar 5 by 5 minus x bar 7 by 7 and so on. 10th is 1 plus x bar n is equal to 1 plus n x by 1 factorial and then minus 1 x square by 2 factorial and so on for x belongs from 1 to minus 1 and should be rational. This means and should be rational, and rational means of the form p by q. P by q are co-prime. And last but not the least, 11th is 1 plus x to the power 1 by x is equal to 3 times 1 minus half of x plus 11 by 24 x square and so on. Okay, so moving on to the next page. Now last thing for the day is Maclaurin's theorem. This is Maclaurin's theorem, and for your knowledge, you can also derive all these expansion series by Maclaurin's theorem, but it's better to learn them, and in giving a general advice, you should try to derive them so that you may also remember them as quickly. So moving forward, it states that the general function, any function of x, can be represented as f of 0 plus x times f dash 0 plus x square by 2 factorial f double dash 0 plus x square by 3 factorial f triple dash 0 and so on till x bar n f n dash 0 upon n factorial and so on till infinity. And it is an infinite series, and if we use only generally, if we use 3 to 4 terms for estimating what the function will look like, or what the graph of the function will look like in the neighborhood of the value x, so it is also termed in a Taylor series. And you may notice that here it is a general function of fx, that is the value of function at x equal to 0. This is the first derivative of function at x equal to 0 times x. this is the value of second derivative at x equal to 0, and so on. This dash means, this n means here nth derivative of function. Okay, and also one important point to note that you can also derive the expression for sine square x equal to z expansion by the expansion series by using it as 1 minus cos 2x upon 2, and using the expansion series of cos x by substituting 2x in place of x. Okay, and now the last part of today's lecture is standard limits. Standard limits, it is a very easy topic, but you need to remember this. It is and it is very easy to remember because it is very obvious. That is, limit x tends to 0, sin x by x is equal to tan x by x is equal to sin inverse x by x equal to tan inverse x by x is equal to 1. And important note is that x should be in radians. And for your knowledge, 1 radians is equal to 180 upon pi degrees. And you may need this conversion if in question the angle is given in degrees. Okay. And please note that here if it is x, here it is x, then only it is 1. If for example if we find sin 2x upon x, it would, the value of it would be 2, because then it is sine of 0 upon same 0, tan of 0 upon same 0, sin inverse 0 upon same 0, and tan inverse 0 upon same 0. The zeros should be same. Okay, and second is limit x tends to 0, a par x minus 1 on x is equal to L, natural log of a, and a should obviously be greater than 0. And its special case is limit x tends to 0, e par x minus 1 upon x is equal to 1. And third is limit x tends to 0, natural log of 1 plus x upon x is equal to 1. And it's another case is limit of x tends to 0, log of 1 plus x to the base a is equal to log of e to the base a, and obviously a should be greater than 0 and a should not be equal to 1. And the last for the day is limit x tends to 0, 1 plus x par n minus 1 on x is equal to n. And in general, x to power n minus a par n divided by x minus a is equal to n times a to power n minus 1, and limit x tends to a. So that's all for the day. Thank you for watching. Please comment how you liked it. Even if it is bad, please comment, like, dislike, whatever you like to do. Thank you for watching. Goodbye.